Okay, problems 20.6. So the question is, we want to construct a box of minimum surface area given the constraint, under the constraint that the volume is equal to V. Suppose A and B and C are the dimensions of the box in the three directions. Then we want to form this problem as a minimization problem of A and B and C under a certain constraint. And we want to derive a Lagrange condition for this A and B, for the optimal A and B and C. And the second question is, what do we mean by that a point x star, which is actually a point composed of A, B, and C, is a regular point? Okay, and the third question is to actually compute the A, B, and C. And the lastly, we want to show that the given point we found in here in the step 3 is actually satisfies the second order sufficient condition. Okay, so the problem itself is pretty easy to formulate. We know that we're trying to minimize the surface area. So the surface area of the box is this, just like that. So this is A, this is the B, and this is C. Okay, the surface area is just that, and the volume is just this. That's the constraint. So Lagrange function will be just this, because it's the objective function which we put here, and the difference with 2 gives us a constraint right here, so it's multiplied to lambda. And then we try to solve A, B, and C. So this is the Lagrange condition, right? By taking the gradient of L with respect to the variables A, B, C, and also the multiplier lambda, then we get this. So this four equations gives us the Lagrange condition. So for a point x star to be a regular point, we know that the gradient or the Jacobian of the h, so this is the h function, h of A, B, and C. The Jacobian of h must be full rank. So the Jacobian here, the h is just a scalar vector function. So the Jacobian is actually just a gradient. So it's a row vector. We just need to show that this row vector is a non-zero vector. Okay, so we take the gradient of h, and we get that. So we want this to be non-zero. That means at least one of these three things is non-zero. Okay, at least one of these three things is non-zero. Okay, the third, we try to solve for the optimal solution. We just look at this system, solve for A, B, C, and lambda, and I think it's pretty straightforward to show that the A, B, C are all equal to the cubic root of V. Okay, meaning you're actually constructing a cube. And in this case, when the A, B, C are like this, then you plug this back into that, you see that this is definitely a non-zero vector. Okay, so it's rank 1, and that means this point is indeed a regular point.